So the first note is that, like pi, e is an irrational number. You have an e button on your calculator. It is right above this ln button. It says e to the x power, so you need to use your second key and then hit that ln button, and you have e to some power. Now, I'm just going to raise it to the first power so that you can see what the approximate decimal answer is for what that value is. E is approximately 2.7. This tells you 2.72. Okay? What's pi? 3.14. Okay, and this is used a lot in exponential modeling, so there's formulas that use e quite a bit. So when there's a base of e, so if I were taking log base e of 7, let's say, you won't ever, you definitely not on the regions, maybe certain times on homeworks if they're trying to get you to figure something out, but you really won't see log base e. Instead, you would see ln, which is called the natural log, which is right here in your title, ln of 7. And actually, there's a reason why the e to the x button on your calculator is the same button you would use for ln, because they're kind of inverses of each other in a way. That's the exponential, e to the x, and that's the log version. That's log base e. Okay? So you won't see log base e. If you do, you have to know that it's the same as the natural log of 7. So knowing that, what is the natural log of e? If I think backwards, since natural log is the same thing as log base e of e, Andrew, 1. Because e to what power is e? So the natural log of e, if you were to type that in on your calculator, the natural log of e, unfortunately your calculator doesn't do e without raising it to a power, so we'll just do to the first power. The natural log of e to the first power is just e, because that's log base e of e, and it just cancels, so it's just 1. Okay? Okay. This is still an exponential function. The exponential functions we have looked at have been 2 to the x power, 3 to the x power, 4 to the x power. So what? This is 2.7 to the x power. Which one of these graphs is an exponential? There's 2 of them that are exponential functions. Which 2 are they? 2 and 3. And since this base is 2.7, should it be exponential growth or decay? Growth. So is the answer 2 or 3? 2. Because this is a quadratic, so that's out. Exponential growth, exponential decay, so that's out because this base is greater than 1. And this is a, what type of function? Polynomial. Specifically, is this odd degree or even degree? Just to review. Odd degree, very good. How about odd function versus even function? Forget about degree. We know it's an odd degree. Odd function versus even function. Does this have any important symmetry? Does it? Is it symmetrical to the y-axis? No. Symmetrical to the origin? Let's see. Does that look exactly the same right side up as upside down? Not exactly the same, correct? So that's not odd either. So this function is neither. This one's neither. This one's neither. This one is even. Okay? As far as talking about back to degree, the fact that this was an odd degree, you can't talk about degree with these two because they're not polynomials. This one we can talk about degree. Based on the end behavior, what's this? Even or odd degree? Even. Quadratics are technically polynomials. They're just a special type of polynomial that we do a lot more with than these. Alright, so let's jump down to the bottom here. A population of llamas on a tropical island can be modeled by. This part is nice because they always give you the formula. So the population is P, given by 500 times e to the 0.035t. I know that's tough to read. where t represents the number of years since the llamas were first introduced to the island. So how many llamas were initially there? They should not tell you t equals 0. You should know enough to plug that in on your own. If they want to know how many were initially on the island, that's year 0. So you're just going to plug in a t of 0. Just type that into your calculator. Well, that's funny. Don't type it into your calculator. Stop right there. Don't do it. 0 times anything is what? Okay. Anything to the 0 power is what? 1. 500 times 1 is 500. So guess what? Just like in the formula that we had been using, with that lowercase a and the uppercase a, that's your initial amount, 500. Part B is where we're going to use a little bit more of our log stuff, I think. Algebraically determine the number of years for the population to reach 600. So where's that 600 going to go, Connor? In for which letter? No t is time. We're waiting for the population to reach 600 for p. So 600 equals 500 e to the 0.035 t. Step 1, Grace? Yep. So that's going to be 1.2, I think. Yep. Okay, the variable is locked up right now in the exponent. So, prior to today, we would take the log of both sides, right? And you can still do that. But now we've kind of talked about, well, you don't have to take log base 10 on both sides. You could take log base 2 on both sides or log base 3 on both sides. In this case, because the base is e, it would make sense to take log base e on both sides. But log base e is the same thing as what button? Log base e is the same thing as ln. So you will just take the natural log of both sides. And what's good about that, again, just like log base 2 of 2 or log base 5 of 5, log base e of e cancels. It's 1. So you just have the natural log of 1.2 equals 0.035 t. And then we just get t all by itself. Divide both sides by 0.035. So the amount of time this is going to take is the natural log. Now again, remember that when you do natural log, it opens parentheses. I only want the natural log of 1.2. So I got to close my parentheses first and then divide by 0.035. And my time to the nearest tenth is 5.2. So don't do it. Don't write this down, but let me just show you something real quick. If I didn't know about this log thing, this log base idea, I could just take the log of both sides. I would get log of 1.2 equals 0.035 t log of e. I would have to divide both sides by the log of e. So I'd have log of 1.2 divided by log of e equals 0.035 t. Divide by 0.035, divide that by 0.035, and type that in. So this just would be a little bit longer. Log of 1.2 divided by log of e to the first, all divided by 0.035. And I'll get the same answer. Okay? So as long as you take the same log on both sides, you're good. So it can always be the plain log. But obviously that just takes a lot more writing and is a lot longer. So if you're trying to get rid of an e, natural log. Okay? All right. So just on your calculator, we're going to skip this part. You're just hitting all these numbers. Oh, no, let's do it. And maybe we don't even need to. What is the ln of e? Did we already talk about that? Log base e of e is 1. Log base e of 1. So think about the what power function. E to what power is 1? 0. E to the 0 power is 1, and you could confirm on your calculator that the natural log of 1 is 0. This is technically log base e of e to the 5th. What's that going to be? 5. Because ln and e's cancel. And what's this one going to be? Without typing it into your calculator? The square root is the same thing as what? So what's that going to equal? 1/2. Okay? Andrew. Yep. No, so what happens is it's e to what power equals e to the 5th. E to what power equals e to the 5th. So, it's like we would take this 5 out in front first as well. Like from that exponent log rule, remember that? Where we can take that 5 out in front, so it would be 5 times log base e of e, and then they cancel. They really technically don't cancel until that 5's been brought out in front. But it seems like a kind of a, I guess, an extra unnecessary step if you just kind of say this cancels and 5 is just your answer. Does that make sense? Okay. Good question, though. So it doesn't become the new base, I guess. So those rules that we learned before breaks about logs and how to expand and condense, natural logs are still logs, right? So division turns into what operation? Do you remember? Subtraction. Very good. If we're going to expand that, the division turns into subtraction. And what do you then know about the natural log of e to the 2nd power? Your 2 can come out in front, and then what's the natural log of e? 1, so that really just cancels. So this whole part is just 2. And then what can we do with this guy? Bring it out in front. So it's 3 ln of x minus 2. Is it? Shoot. All right, and then part A here. We're given information about a hot liquid that's cooling. Its temperature is modeled by this function. T is temperature. M is the number of minutes we've been cooling for. So that exponent says negative 0.03 M. Okay? Without plugging in 0, it's a good question. Without plugging in 0, can someone tell me if they think they know already what the initial temperature is? Nate? Excellent. Explain to everybody how you got that. No, I'm saying without plug. Oh, did you mentally plug in 0? Oh. Which is fine. Right. Right. So without that vertical shift up 67, that 101 would have been your y-intercept, right? So that would have been the initial temperature, but then it just got pushed up 67, which was 101 plus 67, which is where he got the 168 from. Obviously, plugging in 0, your calculator or your mental, you can do the work in your head for that, but I wanted to kind of bring that graphing approach into it. Nate? Absolutely, yep. 67 is room temperature. Because normally, your exponential asymptote is right at the x-axis, right? Think about your parent graph. Normally, that's your y-intercept, or your asymptote, y equals 0. this all got shifted up 67. And actually, you know what I should do? It's not exponential growth, it's exponential decay. And I know that because it's cooling, number one, but also if we typed in e to the negative 0.03, we'd get a number that's less than 1. So I know it's actually decaying. The temperature is starting at 168 and it's cooling down towards 67. Okay? This here means that after 60 minutes, see how 60 is in for your M? The temperature at the 60-minute mark is 83.7. That's what that means. 60-minute mark, temperature is 83.7 degrees. So after an hour, it has cooled down considerably from 168, but it's still not room temperature yet either, right? Think about putting, and I'm going to go back to that exponential decay graph. Think about putting a hot coffee or something from the microwave on the counter. It's going to cool down pretty quickly over the first 5 minutes, right? But it's still going to be warm for like maybe an hour, 2 hours, right? It still won't be room temperature for a while, but because the difference